So in turbulence, we've already seen that there are variables which are fluctuating, and typically the variables we are concerned with are the velocity components. We are concerned with pressure fluctuations, with temperature fluctuations, and so on. Okay, and the definitions and whatever we will discuss in the following, much of it has been actually borrowed from theory of random variables and stochastic processes. Okay, so we have something which we call as a moment. A moment of a variable is something which we will use often in the description of, which we use often in the description of random variables and stochastic processes as well, and it will be of great use in describing turbulent signals. Okay, so if theta is a given random, if theta tilde is a total total variable, okay, then it can be decomposed into theta bar, which is the average, okay, and theta, which is the fluctuation. It can be split into this kind of thing, and theta has a zero mean. So why does theta have a zero mean? Because theta tilde minus theta average is equal to theta. So now if you take an average of this, so by definition theta tilde average is theta average, and theta average is again theta average. So actually this is this. So this is equal to 0. So the fluctuation in, what am I writing? Yeah. So the fluctuation in the variable when averaged, it is 0. So this fluctuation is said to have zero mean. Now a precise definition of moment is dependent on the definition of something called as an ensemble average. So an ensemble average, so what is an ensemble? Ensemble is a collection or a series or a set of repeatable experiments. It is a set of realizations. Okay, so if we say that we have n realizations, if we say that we have n realizations, then the ensemble average is the average of a given variable over the n realizations as n tends to infinity. In particular, the mth moment of the variable u, which can in general depend on x and time, is written as um x comma t. So u to the power n. Okay, you are taking the mth moment, meaning u to the power m of x comma t, and it is defined as limit n tends to infinity 1 over n summation of u x comma t for the nth realization. So this colon n means this particular signal for the nth realization. Okay, but this entire thing has to be raised to the power n, and the summation of n goes from 1 to capital N. So this is what the formal definition of a moment is in terms of an ensemble average. So obviously when m is equal to 1, you get the average, you get the mean. Okay, so when m equal to 1, you have this equal to lim 1 over n summation of u x t n. So all the various signals u evaluated from all the different uh, ensembles, that all the different experiments that you have done. So all the ensembles, they must have repeatability. You cannot have an experiment as a part of an ensemble which is not repeatable. So the experiment has to be designed in such a way that all the conditions can be maintained while taking the readings. So while we take the reading of U, all the other conditions like the boundary conditions or the temperature, so they must be kept more or less constant. Only then we can say that the equation has proceeded, or the process has proceeded under the same governing conditions, and yet it has yielded us a different signal, and that is why you are forced to take this kind of averages. Now when the signal is time independent, so such a process, okay, so such a process is called as a stationary process. So an example of a stationary process is this. So there are some fluctuations, but on an average it remains fixed. An example of a non-stationary process is something like this. So it's like a temperature you are reading at night or just before evening to night transition. And this could be the signal at 12 noon, because the air temperature is not changing a lot, but it is fluctuating because of the wind and all these things. Okay, so this is called as a non-stationary process. This is called as a stationary process. And such time series, when you do it, they are called as processes. In the language of stochastic process, these things are called as processes. So there are various kinds of process. There is a Wiener process, and there are many other, I mean, depending on the statistics of it. So when the process is time stationary in time, we can define, so um, when you do this, is equivalent to writing down this. So this is the average of u to the power m, and when the process is stationary, you can equivalently do this 1 upon delta t integral t minus delta t upon 2 t plus delta t upon 2 u of x comma t dt. So the fluctuation is averaged, and whatever the average is, it is independent of time. So this is only dependent on x. And obviously there are various conditions that must be on delta t. So what is this delta t? It is the window of integration. So delta t is like the window of integration. So if I am sitting over here and my window is this large, so I am able to capture enough fluctuation. So it has to capture enough fluctuations, but it must not be too large. If it is this large, then you are actually smothering out these valleys and peaks. If it is too large, then locality is lost. So there must be an appropriate window of integration, and we'll see this in a problem. Similarly, if the process if the variable is homogeneous, if u is homogeneous, it means that u x comma t and u x1 comma t, they are having the same statistics. So then you can estimate an average through this means. So so once you average, if u is homogeneous, once you average, then it should not be dependent on x. If a domain is homogeneous, it should not depend on what x you have. So the moments should also be independent of x. So this can be defined as 1 by v integral of u to the power m x comma t dx. So dx vector is tantamount to dv. So this is the same as dv, and it is integrated over a large enough volume. So once again, the window of integration for this kind of an integral, it must be large enough to capture fluctuations. So as you can imagine, if this is x and this is the variable, so the variable can have some fluctuations, but the average quantities are sort of invariant in space. And how do you find that average? You have to choose windows of integration. That is quite obvious. You have to choose windows of integration and then perform the integration to find out the average distribution. Okay, so such kinds of averaging, they are sort of commutative. In the sense that del t of u to the power m, so mean of u to the power m, the mth moment, or in fact let us write it like this: the entire average of this. So by definition, this will be equal to 1 upon n summation n equal to 1 to n del t of u to the power m. Okay, this is by definition. And now we can simply swap the differential and the sum. So this is del t 1 upon n summation of u to the power m. So this becomes del t of u to the power m averaged. So the mth moment, so derivative of the mth moment, so the moment of that is equal to this. So we are able to show that the differentiation is commutative. Similarly, you can easily show that multiplying by a constant, then time integration, addition, okay. So all these things are sort of commutative. But multiplying by another signal is not commutative. So multiplying by another signal, so um rather uv mean is not equal to u mean v mean. This is not true. Also, yeah. So such kinds of operations are not true. In fact, they the fact that they are not equal, they lead to various kinds of non-trivialities in the stress decomposition that we will study in the forthcoming lecture. So as we have discussed, the simplest I think